One of the interesting features that we see in biological entities, for example, cells, is their enormous robustness. Cells and organisms have been often compared with machines, and we could actually say that in a way they are machines. They're made of parts, and working in a way requires that all the parts altogether function properly. But in a standard machine, if something fails, typically the machine fails. Within cells, for example, we see a number of mechanisms that are ongoing all the time. Remember that a cell is not really a mechanical object. It's more like a hugely crowded system where many, in terms of thousands of molecules, polymers, organelles are working all together in parallel all the time. There are a number of things we can see, at least in the classical view of molecular and cell biology, that have to do with change of events. All right? For example, in metabolism, we can think in change of reactions that are part of the whole metabolism that require the intervention of a number of enzymes, right? And if that change of reactions is not supplied or not complemented with anything else, every single part of the reactions are necessary. So all the enzymes have to work. Okay? We have a linear change of events. The same happens, again, in the classical view, when we see, for example, how signaling networks work, right? We have proteins in the membrane that act as receptors responding to sensor molecules, right? That change the configuration. This is a whole molecular bunch of details that we are skipping here. But then you trigger events like phosphorylation cascades, right? That, on a first approximation, you could think it's a linear phenomenon, right? We'll go back to that at some point because these cascades, right, usually involving three components in the chain, have a very fundamental meaning in terms of how cells try to perform computations. All right, if everything fails again in these chains, nothing will happen, right? Which is kind of a picture that suggests that the system might be fragile. But biology is not fragile. And the reason of that, and I'll try to show you with the most simple models that we can use, is that biology is largely parallel. Things happen in parallel, right? And that provides a source of robustness, right? Of reliability, okay? That we can show mathematically how it originates and why the combination of different parts ends up into something that it can be extremely robust. All right? Our first step here is use a very simple model, right, to describe the idea of elements working on series, right, working on a chain, a linear chain. And the simplest example, right, is a circuit, an electric circuit, right? We can put here an output, could be, for example, a light bulb, right? That will be our output that tells if things work or not. And then, right, we could put, for example, two switches, right? And we know this is very easy to catch. We know that the two switches have to be closed so that the circuit works. And we can see the output, right? For example, the light bulb being on, right? If any of these is open, nothing is going to happen, okay? That's a series circuit, right? That shows our first picture of why this can be fragile. That is a system that requires all parts working, right? Unless that happens, the system fails. This can be generalized, right? I could think in a circuit with many switches, right? Just to plot it in more mathematical terms, right? I could have a collection of switches, right? Close the circuit, right? And every single circuit here, sorry, every single switch, let's say this is SK, needs to be closed so the system provides the right output. Okay? So let's think in this in more abstract terms. We don't have to be talking about switches, maybe these enzymes here, right? Or the molecular events that allow the phosphorylation cascade to work. So in general, I could think in a system that is made of a number of parts. Again, complexity, right? The parts in the system. So that if I label these as S1, S2, Sn, right? I have a set of n subsystems, right, that operate in some way, and my system overall, right, which I'm going to call S, okay, is what I want to know. When is it going to work? When is it going to properly function, right? Depending on what happens with the units, right? I want to create a mapping between the behavior of the units and the behavior of the system, okay? So this kind of problem inspired in the 50s mathematician von Neumann. We'll find him several times in this course to think about precisely the problem of, he was working on the first computers made of balls, huge systems, and they faced the problem that pieces of the system, like a light bulb, for example, or a vacuum valve, could fail, and then the system fails. And at that time, it was already known that in the brain, you can lose neurons that can die, but that doesn't seem to affect the behavior of the system. So von Neumann actually thought about the question of what do you need to have a reliable computer with unreliable parts, right? And we will not follow the reasoning of von Neumann, but we will see why having a parallel behavior can partially solve the question, right? So let's take this system, okay? And to formalize this, to make some mathematical model, we need to define a number of things, right? The first is the following. We'll say F, right, means that, let's say Fk, that means that the Sk element in this chain properly works, it functions, right? It functions properly, right? And we'll write down the opposite event here, right, like in logic, when Sk fails, right? So using this formalism, we could also write F to indicate that the system works, right, and F with a bar that the system fails. So how can I calculate the probability that the system works, right? Given what? I'm going to call this here probability that the system functions, right? That S functions, so the system is working. And what do I need to calculate that? Well, before I do anything, clearly, if I have this sequential set of events, knowing that if just a single one fails, everything will fail, I know that I need that each one of these elements functions, that they work, right? So this probability is the probability that that the first element is functioning, right? And the second, and the third, and everyone else. There's a number of ways of writing this down. For example, this is one way, saying that F1 and F2 is another notation that is used that works like this, right? And in general, I need that all these elements are going to work. That's a very general picture. Assumptions. One assumption is that the functioning of each one of these elements is independent. If I fail independently of anyone else, right? That makes the calculation, as you will see in a moment, easy, okay? Before I do that, this can be written in a compact form, right? Just for the record, it's important to use this kind of notation as we use the sum of from k to n. We can use this intersection, saying that this is the condition that everyone, right, is necessary for defining our probability, right? Everyone has to function. Okay, now, the simplest way of providing a measure of reliability for single units, okay, is to use just a probability over a time scale. We are not using time here, but we will at some point. Over a given time scale, a year, an hour, whatever it is, right? So everything will be related to that. We can say that the probability that an element functions, right, is a number between 0 and 1, okay? So I'm going to use this. Pk is going to be the probability that the kth element works properly on the time scale I'm defining, right? If that's the case, and under our assumption of statistical independence, everyone has to work, but independently of anyone else, this condition here means that the first has to work, the second has to work, etc., 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 right? So I will have this. Let me write this down here. I will have the product of probabilities, all right, because just independent events, all right, which is nothing but, using this notation, this product, okay? So that the system works requires all these events to happen, and so I have to make the product of all its probabilities, right? Again, this can be made compact, right? In the compact form, this is the product from 1 to n of all these probabilities, right? Okay, we have it, right? The probability that the system functions depending on how reliable are all the elements, right, is this. So we have a relationship between the system's behavior and the behavior of the units on the simplest mathematical form, okay? To see more clearly in a more intuitive way what's the meaning of that, okay? Let's make an assumption. Let's suppose that Pk is the same for all the units. All the units are essentially either the same or have more or less, for all of them, okay, more or less the same probability of failing under the given time scale, all right? Okay, if we use this result, we are saying that I'll take the products of P1, P2, P3 to Pn, but if all of them are equal, right, under this assumption, the probability that my system works, it functions, is nothing but P to the n. This is, on the simplest approximation we can take, the probability that a linear, a series system where you have a chain of events that has to happen is going to work. When we apply that to different problems, the condition that is a linear chain of events can be totally relaxed. What we essentially say is that for something to happen, I have a set of conditions that have to be fulfilled, all of them, right? And so it doesn't need to be a linear chain of events, okay? But let's take this following our example. So what's the meaning of that, okay? And to see that, we just need to plot in a diagram. Well, here I put the probability of my units to work. So this is at the level of units, all right? And here I will put probability that my system functions. So this is the system level, okay? And this is exactly, if you think about it, the way to provide a first approximation to von Neumann's question. What's the probability that the system functions, taking into account that the subsystems are not reliable, right? This provides a measure of how reliable I am. If this is small, the units are going to fail easily. If it's large, they will function pretty well. So everything that happens, it's confined, because these are probabilities, right? It's confined to this square. Everything happens in this domain, okay? So this is our diagram, and for different values of n, for different system sizes, I can see, I can check how does it look like, right? And what's the impact of having more and more elements in the system, all right? So this would be the simplest case, one element. One element means that the system and the elements is the same thing. It's just one unit, okay? And this is, of course, obviously is a linear connection, right? The probability of the system is the probability of the units. What happens when I have two elements, right? For two elements, I'm going to have p squared, so a parabola. And you already see what that means. You see that there's quite a movement in this direction, right? Here is a penalty into having two elements. Right? I lose probabilities. The probability the system functions goes down, right? Following this mathematical curve, right? That would be my two-element system. So it's a penalty for being sequential or requiring that all the elements work. And that gets worse and worse because this is a polynomial relation. You know? What happens with three elements, p cubed? Well, that is much more easy that if someone fails, the whole system fails, right? And even for small numbers of units, you will see, I don't know, for maybe 6 units, that is going to be quite terrible, right? Unless you really have an extremely reliable set of components, right? The system is very likely to fail. So that's not what clearly happens within cells. Even if reactions were linear like the ones I described there, right? Within cells, when things fail, because you have this parallel set of systems performing in different parts of space, and space is part of the story here, right? The embodiment, you can maintain phenomena going on. But that means that my picture here, this set of events that have to happen, is not appropriate, right? To actually make the equivalent model for a parallel system, I need to consider another class of circuit. Let's go for it. Now we've seen that it's easy to make a formal model of a system made of units that operate in parallel, in series, right? As a sequential chain of events. But what happens with this is not the case when we have alternative paths working in the same system, right? For example, in this linear chain of events I wrote here, imagine that there's alternative paths for connecting different molecules within metabolic systems. Like, for example, let's consider that there were another path here where A gives B prima and then C prima and D, right? And that will be catalyzed by other enzymes. So if I think in terms of when is DB properly synthesized from A, I have to consider more than one path here, right? And so the simple chain of events is not going to work as a model, right? The same happens with signaling networks, right? When we look at the real signaling cascades, we see that they can interconnect between them, right? And so the linear idea, the linear picture is no longer valid. Going back into the assumption, so the conjecture of von Neumann about whether maybe computers could be inspired in brains to make computers more reliable when parts of the system failed. If you look at the neural network, again, right, that is kind of the best example of parallelism, right? We can think in a neuron. We'll go for that when we start our part of the course of mathematical neurobiology. But essentially, a neuron sends signals to others, right? And I just plot here 2 neurons that receive inputs from this one, but could be thousands of them, okay? And then these ones also could converge into signaling together into another neuron. So again, the linear picture, gets distorted because they have actually several paths. How can we represent that again in a simple mathematical model, and what are the consequences? If we go back into the electric circuit metaphor, it's easy to actually see how to do it, right? Imagine I have a circuit, right, where my switches are now in parallel, right? They're not following the same chain, right? If I write down again my circuit, that could be my output, right? Like the light bulb. Have my source of power here. And this could be 2 switches or many of them, no problem. This could be the first one. This could be the nth one. And in the middle, I could have many others, right? So if it would be the kth switch. To make it a complete mapping with the previous example, okay? So I can ask again the same question. What happened here now when units fail, right? Each one of these elements, right? Switches is just our first approximation, whatever they are, right? What happened when they fail? What's the impact on the system performance? So again, I'm going to make the mapping into an abstract system where I have a set of units, right? Somehow working in parallel, operating following independent paths. And my question is now, if my system is this, right, S, and I have elements, a set of elements, let's write it down like this, sorry, SK, right, whatever they are. Again, I want to know what's the probability that the system works provided that I have information about the reliability of the components. How can we do that, right? Let's follow the same strategy as before, the same kind of formal approach, okay? I want to calculate the probability that the system functions, okay, that it operates, all right? So now we can see that the situation is a bit different, okay? Because how can I know it's going to work? From here, it's obvious that I just need one switch to work, right? And the system works. If my performance is measured by whether this is, for example, a light on or off, right? Just one switch, it's fine. But 2 switches might be fine. If I have 50 of them, there's a huge number of combinations. And to calculate a probability, I should need to actually know all the possible probabilities for all the possible combinations, right? Looks like quite a cumbersome problem. But actually, there's a very simple trick that allows us to solve it, right? Look at this. This is, in fact, its probability is 1 minus the probability that the system doesn't work, right? Probability of systems failure, right? Okay? So why systems failure? Because there's only one way in which a parallel system, as I have shown here, can fail. It will if every single unit fails. Okay? So how do we calculate that? Again, following the same kind of scheme we have used before, that would be the probability that S1 fails, S2 fails until the end, right? So it's a probability that, let's do it like this, F1 fails and F2 fails, and so on. Okay? You see that this is something that we can easily calculate because it's just a chain of, again, independent events, all right? Now the only difference, right, is again, if we want to write down this is just this here, right, but for failures, okay? But the important thing, if we assume independence, I can calculate this probability as the product of all the probabilities of failure for 1, 2, 3, etc. And that's not difficult to do, because if again pk is the probability that the kth element works, right? This is the probability of failure of the kth element. So this is the probability that the kth element fails. Okay? This is just a chain again, right? We need to do a condition that we can calculate, right? We don't need to have to do all the stuff here. This is just in general this, okay? I don't have to consider combinatorics at all. And this is our general result, right? And for pk equals p for all single elements, or from 1 to n, then the probability that my system functions, right? The probability of reliable functioning when subunits are unreliable is this. This is much compact. And we can work with that. And again, as before, look at what's the meaning of that. What happens when I put more and more elements in the system, right? An important point to make. This usually in engineering, in general, and in biology also, we are talking about redundancy, right? We have multiple ways, okay, of ensuring that some functionality happens. In this case, in the circuit, you have multiple switches that can allow the circuit actually to be closed and function properly, right? It's in a way, it's an insurance that if one part of the system fails, the whole system remains there. And although this is an extremely simple diagram, that's the logic that we use in planes and satellites that are sent to explore the solar system. You have redundant parts that guarantee that the failure happens is not a failure in the system. How does it look like, right? Let's do some drawing. As before, my diagram represents the probability that systems behave properly compared with the reliability of its parts. And again, we move in this square. So, how do the diagrams will work? Remember that for serious systems, the probability of functioning went down, right? Easily, because the more units were added into the serious system, the more and more in fast decay of reliability happened. Here, of course, just the opposite. This case is exactly the same as before. N equals 1, the system and the units are the same. But now, if we plot this, okay, you can very easily show that you have a behavior like this. This is for 2 units, right? N equals 2. You see that there's an improvement. It's more reliable as we add elements, right, that create these alternative paths. Okay? And again, because this is a polynomial, this changes dramatically with n. For 3 elements, right? Here, we have a rapid increase in systems reliability, all right? Despite that the quality, the elements are cramming, they are not really reliable, right? But you see the power of having redundancy in the system in terms of parallelism. And of course, when you use even a small number of elements, right? 6, 7, etc., what you see is kind of a dramatic effect, okay? What is the lesson from this? Well, we just illustrated the point that having parallel trajectories in my system, having alternative ways of performing functionalities, right, that allow the system actually to have different processes happening all the time, even in this simplified picture, okay, provides a source of pretty extreme increase on the performance of the system. The system becomes likely to work in a reliable way, okay? This will have a lot of consequences, okay? One thing that you can actually ask yourself is, what happens if I move from this dichotomous picture, series, parallel, right? It's very easy to actually work out the combinations, right? And as you will see in another lecture, some combinations are really interesting to actually explain phenomena that we observe in natural systems that combine both things, right? For example, if you just want to calculate this, I'll just give you this example, right? Imagine I have a system that combines in series, right, 2 parts. Let's say that is S1, S2, S3, right? But it's a combination of series and parallel objects, right? How can I proceed? It's quite easy, because actually what we just used is a framework that can be combined also in simple ways. Imagine that I think in this as a system, like a subsystem, which I'm going to call M. The reason of calling M is I can think this is kind of a module. And modules, as we also discussed at some point, are an extremely important part of biological design. Right? Subsystems that have internal structure. Okay? So, what's the probability that my system, now my system is all of this, all right? This is my system S. But look, it's very easy to see, because the probability that my system works, that functions, is the combination of 2 subsystems, right? I could say is the probability that S1 works, so F1, right? Multiply it, because it's in series, right, by the probability that M works. Let's write it like this, that the module M functions, okay? So this is just one element, right? So we P1, okay? This is a combination of 2 elements in parallel, right? But if you look at this, at the general expression that we just derived, this is just 1 minus, right? And I have 2 elements, right? If you want, we can use the general form. It would be 1 minus the probability that this functions, so S2, oops, sorry, F2, all right? And the probability that S3 functions, okay? That's from the general expression, all right? So if we make the assumption, to make it simpler and nicer, right, that all the P's are the same, right, the probability of functioning of my combined system with series and parallel, right, is going to be P, first element, and I'm going to have 1 minus, right, remember the parenthesis, this would be 1 minus P, 1 minus P, so 1 minus p squared. All right? It's an exercise for you, because we'll go back to that in another lecture, to check out what's the shape of this function, right? How it looks like in this diagram here, right? And you can start thinking about what might be the impact of combining series parallel or parallel series systems. In other words, what's the difference and what is the relevance of having something like this? Let me put the systems like this, right? It will be a series parallel system, right? Or this. What is the difference in considering these kinds of combinations, right? In nature, we find out that some of these particular structures happen to occur, and there's a good reason for that, all right? So what's the use of that beyond what I was just presenting? Well, conceptually it's very important, because what we are seeing here is that by combining systems in parallel, you automatically improve the fiability, the reliability of a system, right? And biology needs that, okay? Inside the cell, in this really cramped environment with a lot of noise, you need that to happen. And you see that cells perform extremely well, right? If they are computers in some way, they have to exploit these kind of features. And on the other hand, we will see that the same formalism will be helpful for us to make theories of several really important problems. For example, how the incidence of cancer changes in time, where here our assumption is that genes, being mutated or not, can be mapped into this picture of subunits that have to work, or in performing a theory of aging, right? Aging nowadays is started to be considered potentially as a disease, right? So something that maybe we can intervene and change. And interestingly, as also we'll see, the way our organism decay and changes in time, right? As for example, measured by the probability of death, surprisingly, is not so different from the probabilities of decay and aging of machines, right? We will compare them and we'll think about what does it mean for us in terms of understanding the evolution of complex organisms and the evolution of aging as a disease.